All right, hi everybody. Welcome to today's session of the Spectral Geometry in the Cloud seminar. Today we have the pleasure of having Phanuel Mariano from Union College. Who will talk to us about a conjecture for Polya functional for triangles and rectangles. As usual, if you have questions during the talk, either unmute yourself or ask them in the chat and we'll relay them to the speaker. Phanuel, the floor is yours.
Yeah, thank you. Thank you, John. Really happy to be here. Thank you for the invitation. This is joint work with Rodrigo Banuelos, who's at Purdue. So I'll start with some preliminaries on some basics that I'm sure everybody knows. And first start with the Dirichlet eigenvalues. We all know, right, for bounded domains. We have this sequence of their eigenvalues for our eigenvalue problem for the Laplacian with zero boundary conditions. And we have this well-known right variational principle, right, for the principal eigenvalue, right, using this Rayleigh quotient, which is really nice, right, for obtaining bounds, right, especially if you want to get inequalities on the principal eigenvalue. For example, right, if you put a test function for the quotient, the Rayleigh quotient, you obtain upper bounds, but there's also new methods in recent years for also using the Rayleigh quotient to obtain lower bounds as well. There's this nice method by Loginson and Sudeja, I think called the method of unknown trial functions, that also allows us to get lower bounds even when you don't know what the eigenvalues or the eigenfunctions are. And the other object I'll be talking about is the torsion function, right? So the torsion function is defined as the unique solution of this Poisson problem with zero boundary conditions as well. I like to think of things, I've worked a lot on probability and spectral problems and that are interested in probability and analysis. So I like to think of things probabilistically when I can as well. And there's nice interpretation using Brownian motion, which is, a stochastic process that's generated by the Laplacian. And so if you actually, if you take a point X inside your domain, and you run Brownian motion, and you run it twice the speed as how probabilists usually run it, just so that it matches with the analyst Laplacian here. But you run the Brownian motion until it hits the boundary, and you look at the first exit time, right, that it exits the boundary, and that's what tau omega is here. And this is a random variable, right? So every time you run the Brownian motion, it's going to hit at a different spot at a different time. And so if you take the mean exit time, right, started at x, that is actually another interpretation of the torsion function, which as it's nice for using probabilistic techniques, or just at least getting some probabilistic thinking in some of these problems as well. And so the other object I'm going to study is the, you take the torsion function, and then you integrate, so you get the L1 norm of the torsion function, and that's called the torsional rigidity, which also has some nice physical and probabilistic interpretations. So as a physical interpretation, you can think of, well known in the theory of elasticity, engineers are sometimes interested in this quantity, because if you take a long rod where the cross sections are given by omega, in some sense, the torsional rigidity is measuring how much this rod is resistant to twisting forces. And so this is a nice physical interpretation where engineers sometimes write papers on this studying the torsional rigidity. But also probabilistically, you can think of this as, well, take the torsional rigidity, divide by the area, right? And that's essentially the average mean exit time. Meaning there's like two layers of randomness, right? So the Brownian motion is random, right? The exit time is random. But then you also let the starting point of the Brownian motion to be random as well. So if you take the starting location to be from the uniformly over omega as the uniform distribution, then you can think of the torsion rigidity divided by the area as really the average mean exit time, right? So another way of thinking of these, except now there's two layers of randomness in this probabilistic interpretation. Um, so, uh, well, we like to, get some connections between the principal eigenvalue and the torsional rigidity, which, goes back to really, back in the 30s and 40s, where many authors started to study the different connections between the principal eigenvalue and torsional rigidity in many different papers. But in one of them, in 1947, I think at least this is one of the first times that we can actually see this in print. This following functional f here that we define, which is the product of the principal eigenvalue times the torsion rigidity, which is normalized by the area. You can also think of this as the first Dirichlet eigenvalue times the average torsion function, right? As well. So you have these two quantities here, and you can, it's not too hard to see that this is scale invariant, rotational invariant, translation invariant. Um, and you can actually study a whole family of scaling varying functionals as well. And you can look at different powers. And for example, this is one example of a different family of functionals that you can study, where you have the power on the torsion rigidity, this Q here. And you can also look at different operators, more general operators as well, right, such as like a P Laplacian, a fractional Laplacian, or things like that. And but we're in this talk, we're gonna really just focus on the power just one, the Q is just one, and really just mainly on the planar case, though you can really study in any dimension here. And uh, so in 1947, Polya, at least was probably one of the first to observe that this functional is always bounded by one. In fact, and later in Polya Segal's 1951, the classical textbook on isoperimetric equalities in mathematical physics, also you see a proof of this there as well. Um, and it's such a nice, easy, really nice, easy proof, that I'll describe it here. And the idea is to, well, you get an estimate, right? If you want to, show this, this product of the principal eigenvalue and the torsion rigidity is bounded by one, then you can actually get a test function on the Rayleigh quotient to get an upper bound on the principal eigenvalue. And the test function you use is the torsion function. So if you use that, because torsion function has zero boundary conditions, so you can use that as a test function. And so plugging that in, right, on the Rayleigh quotient, and then using integration by parts, um, then you get this negative Laplacian term shows up. But then you remember that the torsion function solves this Poisson problem, right? This negative Laplacian equals to 1. So the negative Laplacian term goes away, so that you're just left with the L1 norm of the torsion function divided by the L2 norm squared, right, on the bottom. And then so once you have this, then you just use Cauchy-Schwarz, right? So you just use Cauchy-Schwarz on using on this denominator. You can replace this denominator by this area divided by the L1 norm squared, which basically gives the result. Because if you just rewrite this as the area divided by the torsional rigidity, you get the result that we want, by just moving things around. So it's a nice, easy proof that shows this bound, this relation between these two quantities. And and really, this, Polya has, studied, many of different inequalities, right, for the torsion rigidity and um, the principal eigenvalue. In the 40s and 30s, you looked at different inequalities involving other physical and geometric constants, right, such as like capacity and moment of inertia, different, connections between different geometric um, constants like area, perimeter, and things like that. So there's, this whole slew of literature in the back, since the 30s and 40s and 50s, and different isoperimetric inequalities, right? Since then. And so, once you have an inequality, right, the next question you ask is, is it sharp, right? Do you have sharp constants? Um, and in fact, in recent times, 10 years ago, in 2015, then you started a series of papers where people have started to ask about these sharp constants for this functional of the product between the Dirichlet eigenvalue and the torsion rigidity. So in fact, the first paper here, Vandenberg, Butazo, and Velichkov, they observed that the zero, which is a trivial inequality, right? That this function is always positive, right? But they showed that that's actually sharp for overall open sets, right? So and the idea was to get you always usually get some, either you find an extremo or you find a sequence of domains that approach that constant. In that case, it was a sequence of unions of balls, of disjoint balls that have certain radius. So if you just get these types of domains, they eventually approach zero, the trivial lower bound. The second paper by Vandenberg, Ferrone, Nietzsche, and Torbetti was gave the show that the one is actually sharp over all sets of fine open sets of finite measure, and that was a little bit tougher. In fact, again, they showed that there's a sequence of domains that approaches this one. In that paper, the domain is more complex. So here sometimes these domains were called Swiss cheese domains. You can think of Swiss cheese domains because it's some kind of bounded domain with several holes, and you just pick the holes and the number of holes just right, so that you're able to get the sequence of non-simply connected domains that actually approach the one. So that was a non-trivial result that showed that that was sharp. Um, so then the next thing is, and then you can ask, can you improve this bounds if you restrict your class of domains? And so naturally you can ask, what about convex domains? So the second paper, Vandenberg, Ferroni, Nietzsche, and Trombetti, they studied convex domains and actually in any dimension, and they were able to obtain sharper bounds. So they were able to improve on these bounds for convex domains. And so I'll just, since my talk is mainly on the planar case, so I won't show what the bounds are that they've gotten for in RD. Um, but the bounds do depend on dimension, right? The upper and lower bounds. But in the planar case, the bounds they were able to attain were the pi square over 48 for the lower bound, and then this constant here, which you notice is slightly less than one, right? It's 0.9999 and some other numbers, and so it's slightly better than one, but it shows that one is not sharp for convex domains. So there is some improvement there. For convex planar domains. And so then the next question was what are the sharp constants? And so and just to note as well that there's recent work done by Vandenberg and Bakul in 2024 just recently, where they also show that if you restrict your class to simply connected planar domains, you can also show that one is not sharp for for simply connected planar domains. So they were also able to obtain a bound that's also just slightly less than one But again, still don't know if these are, what are the sharp results. So now, so now that we can improve these bounds, so naturally, what you ask, what are the sharp bounds for in this convex setting? So I'll state what is the current best results in the literature. So Fatui in 21 actually improved for convex bodies. So he was actually able to improve the only slightly, right, from the 0.999 and some digits and to 0.99, right? Which and so this is the current, as we know, is the best constant for convex bodies, which really shows that how difficult this is, just to get some improvements in the sharp results. That's a whole nother question, right? To actually get the best result. And then for the lower bound, the best results that we know of so far is the pi square of 32. So this was improved to, much better to pi square over 32. And in fact, you can actually, in some sense, you can find this in three different papers. Um, and Della Pietri, Gavitone, Labianco, Brasco, Mazzoleni, and Biani, Butazzo, Prinari. And independently, you can actually find this result either there explicitly, um, either for like other types of operators, more general operators, or maybe there was using different methods, or in fact maybe I think in some of them they were actually studying different functionals. In fact, different functionals that involve, like, for example, the maximum the maximum of the torsion function and the torsional rigidity. There's also other papers that study those functionals by Enroux and other authors as well, that I haven't listed here. But so there's several different papers that studied related functionals as well. I apologize if I'm missing any references here, um, so these other functionals sometimes imply. So if you get sharp constants on those other functionals, you can get you would prove the sharp results for this functional that we're studying. And so so then you can ask, so what is the conjecture, right? So what is the conjecture, upper and lower bounds? And um, and so for bounded convex planar domains, the conjecture is pi square over 24 for the lower bound, and pi square over 12 for the upper bound for convex planar domains. And so different papers listed these parts of these conjectures. And so I think this was the first paper that combine all the conjectures into one nice simple conjecture. And in fact, they looked at for any dimension actually. So there is a conjecture for any dimension, but I'll stick to just the planar case as well. And then and the conjecture is that these are sharp. For example, the lower bound. If you take any collapsing sequence of triangles or rhombi, right, and you collapse them down to an interval, um, that those domains will approach the lower bound of pi square root of 24. While for the upper bound, if you take basically like a elongating rectangle, right? So you just take a rectangle and you just let it approach the infinite strip, that will approach the pi square root of 12, right? So these would be like the sharpness bounds. In higher dimension, the lower bound, these triangles or rhombi can be generalized to like they call it cone domains. If you get the a lower dimensional convex set and you make a cone and you collapse it down, those would be the extremals for the lower bound. And then if you for the in higher dimension, the upper bound would be like the slab, right? So you take a lower dimensional, one dimensional less convex domain, cross an interval, and if you just let the interval approach to infinity, right? Those would be the slab would be the upper bound for in higher dimension. And so the conjecture is actually motivated by in their paper. there was an asymptotic result that actually where they proved for thinning convex domains, and several other papers have studied thinning convex domains. And what they proved was if you take a thinning convex set, right, omega epsilon, which is basically a convex set, bounded by the graph of two concave or convex functions, right? So you take this domain that's a graph of two functions, and you take this epsilon where you can collapse it down again. Collapse these functions down, and then that limit of these thinning convex domains, they prove that that limit is always going to be between the pi square root 24 and pi square root 12. So this is one way which gives evidence for this conjecture. And in fact, they prove that if you take these thinning convex domains, then you only get these are sharp only for the cases of the conjecture above, right? So only if you take the thinning rectangles, you get the upper bound, and then if you take thinning triangles and rhombi, then you get the lower bound, right? In fact, partially these results are also due to some of these asymptotics were due to a paper by Borisov and Freitas from earlier in 2010 and 2013. Now, it's
Sorry,
surprising. Yep.
Daniel, there's a question in the chat asking what is F for the unit disk or for balls in higher dimension?
Yeah, so that's it's I don't know exactly, but it's you can compute it, and there's going to be some terms there. I don't know exactly what it is. Uh I think actually I can probably pull it up real quick. Maybe um,
Yeah, just wondering if it's something interesting.
um it could be computed explicitly, but it's not.
Okay, if it's not something exciting, then we can move on.
It's not something at least that I can't remember off of my head. Yeah, it's like maybe d times d minus 1 or something like that. Yep. Okay. Can you still see my screen, or?
Yes, we can.
Yeah, okay, just making sure. Um yeah, so
Let's move it to full screen mode.
full screen, right. There you go. Awesome. Perfect. Okay, so then for the ball, would be, they're between, these things. So they're not the extremals. At least I can tell you that. And but for a lot of things, it's harder to, for the ball, you can compute things like that, but a lot of things you can't compute explicitly, including for like something like triangles. And in fact, that it's surprising that the conjecture is still open, even for the class of all triangles and rectangles. And so, that's our main result for this talk, is that we were able to prove the conjecture for a class of all triangles and rectangle, and show that they do have the bounds of the pi square root 24 and the pi square root 12. And of course, as we already know by the thinning results, by the earlier papers, right? This is a sharp, right, for in a class of triangles and rectangles. If you just take any collapsing triangle, or any collapsing rectangle, really, you get either the lower bound or the upper bound. And aside from, I'm sure many might know that aside from special cases of triangles, there really are no exact or explicit formulas in terms of like elementary nice functions, right? Or polynomials or something like that, other than just the few examples such as the equilateral triangle, the right isosceles triangle, and the and the 60, 45, 90 triangle. So, other than that, really, there's no exact, nice explicit formulas for these quantities. But there's a slew of wealth of literature of proving inequalities and other characterizations for the torsion rigidity and the principal eigenvalue for triangles and other polygons and such as quadrilaterals. So this list is not at all inclusive. Just some of the ones that I've seen and have been useful, especially in our results. And even some recent results by Emmanuel Andre and several other authors as well have looked at sharp inequalities that are quite useful in these results. And but there is a partial results that was really interesting, which is really the first to get to show any domain to prove the conjecture, the lower bound for any domain, was this result by Vandenberg, Baroni, and Nietzsche and Trombetti in 2020. So they were the first to show that for the special case of isosceles triangles and run by as well, they were able to show the lower bound of the pi-square root 24. So really our result finally completely resolves the conjecture, the lower bound for all triangles really. And so we're able to do that. And in fact our work is the first to actually obtain the conjecture upper bound for really any domain. So that wasn't in the literature before, other than say like the ball or some other things that you can compute explicitly, right? But for things where you can't compute explicitly, I think this is one of the first that was able to show for a class of domains, if I'm not mistaken. And well, to discuss some of the main difficulties here is that really you have these competing symmetries in the problem. And so, I mean, basically symmetry breaking happens here because, the classical symmetrization techniques, they increase the torsion rigidity while decreasing the eigenvalue, right? So you have this kind of like balancing act between these two quantities, right? One wants to go up, the other wants to go down. So symmetrization hasn't really, at least in the usual sense that where people have applied it in many of the past very famous problems, haven't been successful in working for this functional. When you really have a function that involves both at the same time, such as our functional, and because we know, symmetrization techniques have proven inequalities such as Faber-Quandt inequality, right? The Saint-Von inequality, right? That shows that overall domains of same area, right? The ball minimizes the principal eigenvalue while maximizing the torsion rigidity, right? And even Polya himself, right, used this technique for triangles and quadrilaterals, right? This was successful for showing that, this is the famous the Polya problem, where if you look at all n-sided polygons of same area, the regular polygon minimizes, right, the principal eigenvalue, or the regular polygon maximizes the torsion rigidity for triangles and for quadrilaterals. Though this technique does not work for higher dimensions, right? Like for n greater than or equal 5, but just to point out some nice recent improvements for the Polya conjecture by Bogoslav and Bokul, where numerous rigorous numerics have been used. And so rigorous numerics, and it's something I've actually been working on different problems as well, is a nice new tool that could help for these techniques when such as when symmetrization fails for for example when n is greater than 5. And so, but the point is, at present there's really no general techniques that gives the increasing or decreasing for the product, right, as a single union. So when you look at this as a single unit, it's hard because one is going up, the other is going down. So at least the standard techniques don't work, unless you develop a new symmetrization technique, or maybe some other clever way that allows us to study these functionals where you have both of them at the same time. And so So really, our proof is, uses some ad hoc techniques that really gives bounds for each quantity separately through a case by case analysis where we have to really dig deep into the different types of triangles and rectangles. And the hardest part is really showing the lower bound for triangles, right? This is really the biggest non-trivial result is showing for all triangles you get the pi-square over 24 for this functional. So I'll spend the next a few minutes just to give you just a rough sketch of the proof, some of the nice results, and do some advertisement of some inequalities that end up really useful in these types of problems, and maybe could be helpful to you as well in some other inequalities when you're trying to show sharp inequalities. And so the first thing you have to do is, well, let's start with triangles. Let's talk about the lower bound for triangles. You really have to pick a moduli space, right? Some representation for all, say, obtuse and acute triangles and so on. And throughout the talk, I'm always going to pick our triangle to have the vertices at the origin at 1, 0, and some point AB where we vary and get different triangles. So this is like, for example, here, our picture, we get an example of an obtuse isosceles triangle, right? So as you see, we have the origin 1, 0, and AB is the only thing that we're going to be allowed to change. Okay, and so for obtuse triangles, the moduli space that we pick are basically all AB that are inside this quarter circle. Here, it's the circle of radius half here. And so if you range AB anywhere in this gray area here, you get all, by the scaling variance, it's enough to just study basically all obtuse triangles where the AB is in this gray area. Just something to note is this line right here corresponds to the isosceles triangles, as well as these as well. This basically the outer boundary is the isosceles triangles. And this point right here, right at the top, where A is a half, B is square root 3 over 2, that's the equilateral triangle, is right there. Right over here on top of the smaller circle it's the right isosceles triangle, 45, 45, 90 triangle. And this gray boundary here, the boundary of this gray circle, quarter circle, are the right triangles here. So you could break up into the moduli space into a nice compact set. But it turns out just as a matter of convenience in our computations, we're only going to use this characterization for obtuse triangles. For acute triangles, even though the blue actually corresponds to all acute triangles, we're going to use a different characterization for acute triangles, where we look at, again, we still look at vertices 0, 0, 1, 0, and AB, but then we're going to range AB on this infinite strip here, where the A is going to be between 0 and a half. But we're going to look at all points AB outside the unit circle. So this infinite strip outside the unit circle allows us to, just to make the computations nicer, allows us to an alternate way to look at the acute right triangles. And what we do is that we break it up into different cases. And so here are the different cases that we break it up. So for the acute case, so this is the acute case. This is the infinite the strip between 0 and a half here. Equilateral triangle is right there. It's this point 1/2 square root 3 over 2. And case 1, so these are the acute triangles. Case 1 is, I'll call them the nearly equilateral triangles. The triangles closest to being equilateral is case 1. And case 2 is the long, thin triangles. So if you pick AB here, you get a really long triangle. Acute triangle. This line right here, the outer part right here, and this will become useful later, what corresponds to the right triangle. So anything there will be a right triangle on this when A is 0. So these are the two cases for the acute triangles, and the obtuse triangles. Excuse me. We split them up into three cases. So case one are the ones that are the closest to this point right here. This point corresponds to the right isosceles triangle, so the 45, 45, 90 triangle. And then we have case two, which are kind of a mix between some kind of long, thin triangles, and then triangles that are also close to degenerate triangles that are obtuse and close to the isosceles triangles as well. So this, we have to use a different method for the triangles that are here. And then the case three is this green part right here, which are really, very long. The closer you get to 0, 0 to the origin, the skinnier, the more degenerate they get, these triangles. And these are the ones that are closest to really to being acute or right. And so the closest you get to the white part, you really get something that's it's kind of hard to differentiate if it's acute or obtuse. So those are the different 5 cases that we study, and then depending on the case, we have to use different techniques. And then just so you get just a flavor of the idea here is some of the proof strategy is, well, we either prove new or use known lower bounds for the principal eigenvalue or the torsion rigidity for triangles. And then use the fact for this moduli space, the area is B over 2. And so using these bounds, you get this lower bound here on R functional. And in some of the cases, it's are easier than others. Some of the cases you can, just by doing some analysis, you can show the pi square over 24 holds. But some of the hardest cases involve the long, thin, obtuse triangle. So anything that's a kind of a long, thin, acute or obtuse triangle is the most difficult, because those are the cases that are approaching to the sharp constant. Those are the cases that are degenerating to the sharp pi square over 24. So naturally, those are the tougher cases. And just to get just a rough idea is, you get this bound, call it H for now. And for the hardest cases, we have to kind of show that this H satisfies some kind of monotonicity property in some sense. And so just to give you some ideas of some of these bounds that we get. And before I talk about that, so one of the main ideas that we'll see later is that we're going to kind of reduce to the right triangle case. And so that's one of the new ideas, is to actually you get these bounds, and then you hopefully want to reduce to some simpler triangles. So you do some kind of monotonicity and show that it's enough to actually show the bound for right triangles. And then you do some analysis on just right triangles, and then you get your desired lower bound. And okay, so what are some of these bounds that we use? So for example, one of the bound by Sudeja was this bound that actually I'm putting already the simplified version of the bound, but the bound was actually in terms of sectors. So if you look at, what Sudeja did is he compared triangles to sectors of same area. And he was able to show that basically for sectors of same area, and they have the same angle gamma as its smallest angle, the eigenvalue will always be smaller. So it's almost like an isoperimetric type inequality. And then you can compute that in terms of the first zero of the Bessel function. And so these bounds are good for long and acute or obtuse triangles. I guess in some sense, because for really long triangles, it's kind of hard to differentiate between triangles and sectors in some sense. And so this was a really useful bound. Another one that's just it's a really nice, very pretty bound, I think, by Freitas and Sudeja, who proved this lower bound for triangles in terms of the diameter and the height of the triangle. The height meaning the one that's perpendicular to the longest side. And these are good for basically the non-degenerate cases, right? So like, nearly equilateral, nearly acute, or nearly right isosceles triangles. And I kind of want to advertise these really nice bounds because they're really good and really close to the actual values. In fact, they were recently used to prove the Payne-Polya-Weinberger inequality for triangles, right? Which is the inequality where Aschbach and Ben-Guria showed the famous conjecture that if you look at the ratio between the two, the lambda 2 and lambda 1 over all domains, right, that's optimized by the ball. But if you restrict to triangles, the conjecture is, well, if you restrict to triangles, that ratio should be optimized by the equilateral triangle, which in this case you can compute exactly as 7/3. So that was recently done and finalized. It was first started by Sudeja and finished by Arban and other authors in 2022. And then, basically for the lambda 1, you want to show this upper bound, so you need a lower bound, and these were the two lower bounds, the key lower bounds that allow them to get the Payne-Polya-Weinberger Aschbach-Ben-Guria inequality. And so if you ever need some nice bounds that are useful for proving inequalities, these are very good in that case. But for the torsional rigidity, a lot of it we had to come up with brand new techniques or inequalities that weren't known before. It's nice that the torsional rigidity has this variational formulation as well, which allows us, by putting test functions in, to get lower bounds for the torsional rigidity. And in fact, just to give you a little bit, just some of the lemmas that we've obtained that were useful. For example, if you have nearly equilateral acute triangles, right? So triangles that are close to being equilateral, well, you probably want to compare it to the equilateral triangle. So the equilateral triangle has a known, really nice torsion function. So that's known. It's in terms of polynomials, and then you can come up with the test function by using this linear transplantation, where you get this map that transforms any triangle and maps it to the equilateral triangle. And then you compose that map with the torsion function for the equilateral triangle, which therefore gives you a test function, right? Because then you get 0 on the boundary, and then this is a test function for any triangle, basically. But these bounds are really good for things that are close to being equilateral. Not so good if you're really long or thin. But if you compute this exactly, put them into our variational bound and do some computation, you get this explicit lower bound for the torsional rigidity, which tends to be really useful for triangles. And then for nearly isosceles triangles, you do a kind of a similar thing, except you use a different test function. And this test function, you can get inspired by, well, the triangle is bounded by 3 lines, all right? So you can use these 3 lines to kind of guess test functions that are 0 on the boundary. So basically, by playing around with the boundary lines, it's easily to check that this is a 0 on the boundary. And then you can basically use this test function and do the computation to get this inequality. So this is good for things that are like obtuse and nearly isosceles, basically. And so these are just some of the inequalities that are useful in some of the cases, right? So but there's still a lot of work to show actually these the product ends up being good enough for proving the lower bound. So the hardest case is the long case, right? The long acute triangle or obtuse case. I'll stick with just the long acute triangles. Just to give the main ideas. So you pick it to be long enough. So here A is between 0.5 and B, which is the height of your triangle. B being bigger than 3 is good enough for it to be long and thin. And the idea came from this. If you look at numerics, we conjectured actually it's pretty clear by looking at some of the numerics that if you look at this function, if you look at all triangles of fixed height, it turns out that the right triangle of same height minimizes. We conjecture that it minimizes this functional. So there's, in fact, that there's a monotonicity for a fixed B as well. So it seems like it's minimized for a fixed height. It's minimized by the right triangle. And then if that's really true, then all you have to do is prove the lower bound for right triangles. And in fact, there's also this monotonicity for right triangles as well. In fact, if you take B, the height to be really, 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 really big, so as B increases, this functional decreases. And in fact, it's pretty clear that it decreases to the sharp constant of pi squared over 24. So we weren't able to prove this, but we proved the best next thing, which basically, we prove a bound that has these monotonicity properties. And so just to give you just a hint of the proof, a bound for this that we use for the eigenvalue was this Sudeja bound, which is in terms of this first zero of the Bessel function, which you can also give bounds on that, which is given by this inequality by Chu and Wang, which you can actually, because the first Bessel zero isn't explicit, but you can bound it by this nice, explicit formula. And so that ends up being a useful bound because it's kind of like a sector bound in some sense. And then the torsion rigidity, what we do is basically you use domain monotonicity. So you have the regular triangle, which it's just this is the regular triangle here with some height b. You put an isosceles triangle inside it. So you put an isosceles triangle inside it, and then inside this isosceles triangle, you look at the height of the isosceles triangle, and then that means you can put a sector that's inside the big triangle, right? So you can basically find a sector that is inside, and using domain monotonicity, you can bound the torsion rigidity of the triangle by the torsion rigidity of the sector. And then you can you can get some appropriate analysis on this because you have an explicit expression, and then you have to do some bounds, and then you can use this inequality. And so using this bound, you put them all together, and so you have this kind of nasty looking bound. But the idea is really simple as before. So first thing is you look at this map in terms of the angle gamma, which is the smallest angle of your triangle. And then you notice, you have to prove this, but you notice that this is increasing. You have to prove that this is increasing exactly in our range of gamma, which corresponds to the height being big enough. And then you notice that, well, for fixed B, this is just a geometry facts. For fixed B, the angle that is minimized is the right triangle. The right triangle minimizes the angle of the smallest angle gamma for fixed B. And so because this is increasing, you can then reduce the problem to just right triangles. Okay. And so then you have a bound in terms of right triangles. And then you have to do just some more analysis on the right triangle bound. And then if you do that correctly, then you get the bound that you want, basically, and you have the monotonicity. So it's kind of the proof was inspired by this conjecture that we had, where we do kind of like the best next thing for the bounds. And so that's kind of like the main idea of the at least of the proof, is to kind of notice these monotonicity and try to show these monotonicity for these bounds. And so just very quickly, since running out of time here, and the upper bound is much simpler to prove, and it really comes from these two bounds, one by Maikai, which gives a bound for the torsion rigidity in terms of the perimeter and the area. This is sharp. And another inequality by Sudeja, which is an inequality in terms of area and perimeter and the first Dirichlet eigenvalue, which says that this is actually maximized by the equilateral triangle. So using the kind of known bounds, you can actually pretty easily get that our functional is bounded by 2 pi squared over 27, which is basically strictly less than the pi squared over 12, which should be extremal for the rectangle, right? And then for the rectangle, I won't go too much into rectangle, but what we prove for the rectangle is a stronger result. We actually prove a monotonicity property for this triangle. And what we actually prove, and I'll just summarize here, is that basically for overall rectangles, this functional is minimized by the square, which is strictly bigger than pi squared 24. And then it's always less than or equal to pi squared root 12. In fact, we prove a monotonicity property that allows us for rectangles that allows us to get this result. And so I just skipped to just some basic ideas. Is kind of working on quadrilaterals now. It's harder because the moduli space is 4-dimensional, and then basically it'd be nice to see if this can be done, even though the problem is still unsolved for the general convex case, but maybe some if you put some more symmetry to the problem, such as if, let's say, it's convex domains that are symmetry with respect to both orthogonal axis or to respect to some kind of 2 axes. These have been very successful in other problems, such as this recent result by Enroll, Lamont, and Lucadesi for the Neumann Laplacian. And then results on the hotspots conjecture have been really successful when you add some more symmetry to the problem as well. So nice other results that maybe some of these ideas could be useful for, or you can, or maybe new techniques are going to be needed as well. So thank you.
Thank you very much for the talk. So we have time for a few questions. Please unmute yourself or ask the question in the chat. Thank you very much. I guess we had a question during, and your exposition was very clear. So.
Okay. Yeah. Thank you.
Corentin is asking if there are any similar conjectured bounds in higher dimension.
Yeah. So the original paper, the conjecture actually was listed for higher dimension. So with explicit constants in terms of the dimension, so that's I don't remember the constants off the top of my head, but so yeah, I only focus on the planar case, but yeah, so the lower bound should be the obtained for cone domains, and the slab should be the sharpness for the upper bound in higher dimensions.
And does it make sense to explore like the moduli space of simplices or things like that in higher dimension?
Oh yeah. I mean, yeah. I've had some. I've worked on similar functional like this rather than rather than L1 norm. I looked at the L infinity norm of the torsion function, where I've had conjectures as well for like simplices and so yeah, so there are conjectures. I just but for this problem, I mean, like, for example, it's hard for, like, for example, one thing we didn't prove is the upper bound for, like, for example, triangles. And so if you look at if you just focus on triangles, the upper bound over just triangles should be the equilateral triangle. And that's something also we're working on right now. So we were just looking at the main conjecture for triangles and rectangles, but and so you can do similar kind of conjectures. Maybe it's the regular one for for higher dimensions as well.
Thank you.
Yeah, I have a question.
Yeah, sure.
So thank you for the very nice and informative talk. I was just to make sure that I got it correctly. So is it correct that all your bounds, the lower and the upper ones, are done by combining bounds for lambda 1 and bounds for the torsional rigidity, right?
Correct. Yeah. Yes.
There's somehow no other known technique to bound this entire expression, right?
Correct. Yeah. That's
And
the
no
main.
idea whatsoever to do it.
Yeah. I mean, we thought about, coming up with some kind of, you have to come up with some kind of another symmetrization technique or something like that. But that's what makes this really difficult. There really isn't. And that would be something really deep, right, to be able to do that.
I see.
Yeah.
Thank you.
Yeah, sure.
So I think we can thank the speaker again for the great talk. Thank you very much.
Yeah. Thank you.
We meet again next week with a talk by Isabel Fernandez. And in the meantime, have a lovely week.
Thanks for the talk.
Yeah, thank you for the invitation. Nice meeting you all. Take care. Bye.
Cheers. See ya.
Have a love the day.